My colloquium. It is a pleasure to have Professor Marco Merkli for the first talk in this series of talks for our colloquium. Professor Merkli is from the Memorial University of Newfoundland, right, in Canada. Professor Merkli is a leading researcher. His research is in mathematical physics, functional analysis, and quantum dynamical systems, right?
Yes, that's correct.
So, welcome, Marco.
Okay, thank you very much. Thanks very much. I'm very glad to be here. I thank especially the organizers of this colloquium series, David, Bernardo, and Joel, and also many thanks to Eduardo, who is my host here. Eduardo gives me a very good time, especially when we go out for dinners and have maybe a beer and a tequila. And he gives me a very hard time when we discuss mathematics. But I enjoy both, so my stay here is very nice. Thank you. Okay, so you probably don't know, with the exception of myself and one other person in this room that I know has been to Newfoundland, which is in the eastern part of Canada. You probably have never been there. And in case you ever want to go, I make it easy for you. If I can switch to the next page. Oh, here. This is what you have to do. This is the path from St. John's, where I live, to the Sinvestav. Okay, and I put in here the version where you walk. It's about 1,500 hours. So if you walk 6 hours a day or so, it takes, I made the calculation, about 260 days. And I didn't take this path because there are some warnings, okay? And these warnings are, the first warning is this route includes a ferry, because Newfoundland is this thing here. It's actually quite big, but it's an island. So here you have to cross over a ferry. I thought that's kind of okay, I can do that. But the second warning here is this route crosses through the United States of America. And I thought that might be a bit more dangerous. So what I did, I just took a plane from St. John's to a city called Toronto, that's around here, and then another plane from Toronto to Mexico City. Okay, so St. John's is a small city. The island is not very overpopulated, kind of. And when you go about 10 minutes outside of town, then you see scenes like this. It's on the seashore. So I took this picture last summer. There's the sea, and there's lots of hills where you can do nice walks and stuff. And so you see in this picture already, it's very calm. It's very little population. The traffic is not so dense. So if you compare with Mexico City, it's quite different. And this is a picture in the summer, mostly with blue tone colors, but we really have in Canada seasons. And so in the winter, the main color is not so much blue, but it is rather white. Okay, so here's a picture of my wife Nancy, who is going to work. But at night it was snowing, and you can see, oh, this white stuff here you see is called snow. I don't know if you know what this is, but it can become quite high. So here's about, hip high. And when you wake up in the morning after a snowstorm, this can look like this. And so going to work would be this way here to our car, which is over there. And these are the steps of our home. So here's the door right about here. So she didn't get yet very far, maybe 2 meters. And so it's quite a workout to get through the snow when we have a lot of snow. And in fact, the university in the winter is closed usually 2 or 3 times during the winter when we have what's called snow days, because everything doesn't work because the snow has fallen. Okay. No, other way.
We also close some days.
For heat.
Pollution.
Pollution, oh yeah. Well, there is absolutely no pollution here, okay. I have trouble navigating this back and forth thing. Was there a hand? Can we have the next slide? Okay. So I think I know that most of you maybe are not familiar deeply with quantum theory. And so in the first talk, in the first half, or in the first part of my talk, I want to give you a little introduction to quantum theory and give the postulates of quantum theory. And in the second half of the talk, I want to talk about this Quantum Zeno Effect, which is an interesting phenomenon. And so let's start with the formalism of quantum theory. Okay, there's basically 4 postulates in quantum theory. And at the beginning, they may look crazy, but if you get used to them, and it has been verified in experiments that this is actually a good way of describing life, then it's quite beautiful. So the first postulate of quantum theory is that the state of a system, a physical system you're interested in, is described by a matrix, okay? It's called a density matrix. And this matrix is acting, or an operator is acting on some Hilbert space. These are very abstract concepts, I guess, but we will see how this turns into real physics. Okay, so a state is called rho, a density matrix. It's a bounded operator on a Hilbert space. And it has some properties. The operator should be non-negative. This means that all the eigenvalues of the operator should be non-negative. And if you sum up the diagonals, if you take the trace of this operator or matrix, you should get 1. This has something to do with probabilities. Okay, and then you can ask yourself, okay, that's a postulate, but I mean, what does this mean, right? And then physicists, they know for what kind of systems you should take what kind of Hilbert space. For example, if you're interested in describing a spin 1/2, which has up or down, or a qubit, which can be in state 0 or 1, you have essentially 2 states you are in, and so the right space to describe this is just complex number C2 vectors with 2 components, complex components. If you would like to describe a particle that's moving in position 3 dimensions in space, then physics tells you, the right Hilbert space to take is the space of all square integrable functions of position x. If you want to describe a quantum oscillator, the physicist tells you take this space. If you want to describe a quantum field, like the quantized electromagnetic field, there is associated to it a Hilbert space you should take, and this is called the Fock space. So for any kind of systems you want to look at, there is some Hilbert space. Okay? All right. So that is what a space should, what the state space should be. And then you should look at the dynamics, right? Because you're interested in, you have some initial condition of your system, and then something happens to it, and you want to predict what happens in time. And so there's an evolution equation, and the evolution equation makes this state time-dependent. So now this matrix becomes a time-dependent matrix, and its time evolution is given by this differential equation. Take I, that's the complex I, times the time derivative, and this should be the right-hand side here. The right-hand side is the commutator of some other matrix H with a state rho. So this is H rho minus rho H, okay? This is called the Schrödinger von Neumann equation. You can sort of rewrite this in integral form if you wish. The state at time t is obtained as follows. Take the initial condition, the state at time 0, this is a matrix, and you conjugate it with this propagator, it's called, e to the minus ith, which is a unitary group. H is a matrix, t is time, okay? And the generator of this group is called the Hamiltonian. Again, that's another matrix. Well, what should you take for H? Because once H is given, you can solve this equation and the evolution goes on. In the examples I had above, for a qubit, for example, typically what people look at is this Hamiltonian can be just this simple matrix called the sigma z Pauli matrix. If you describe a particle in space which sees some potential, then you get what's called a Schrödinger operator. This is a very famous sort of deal in mathematics and physics. People spent their whole careers examining Schrödinger equations, Schrödinger operators. The Laplacian is just a second derivative, and then you add some potential term, which is a function v of x. And for an oscillator, you know what the Hamiltonian should be. And for a quantum field, you know what the Hamiltonian should be. It's not important exactly what those are. I'm just telling you, if you want to describe a particular situation, then you know what these objects are. So far, there hasn't been any physics, right? Because what? A state is a matrix, you know. This dynamics is like this. Where's the physics? Trying to see? Well, I'm trying. Oh, okay. And the next postulate is the third postulate of quantum theory. It actually makes contact with real life and physics, I guess. And it tells you what it means to measure something, because if you have a particle, you want to know about its position. So what does it mean to measure the particle, the position? And the postulate says every physical quantity, like energy, position, momentum, angular momentum, whatever, corresponds to another operator m. Okay, so all is about operators. It's non-commutative world. And these operators are called observables. And let's say you have one of these observables, maybe one that represents energy. Incidentally, the Hamiltonian that generates the dynamics is interpreted as the energy operator. So let's say you have this operator you want to measure. It corresponds to any physical quantity. And then you look at its spectral decomposition. I just write this down here for finite dimensions. But this matrix can be written as a sum of eigenvalues times eigenprojections, right? That's just the spectral representation of a matrix, the diagonalization of a matrix. And then the postulate of quantum theory tells you that when I measure the quantity m, for example, energy or position, the only possible outcome I can get, the readout when I measure, is one of these eigenvalues mj. Nothing else I can ever measure. Okay? And it's very crazy. So which one, if I have a state rho, and I make a measurement of the observable m, what will be the outcome? What will I measure? Which eigenvalue will I measure? This is random, okay? This is a random quantity. So you measure the quantity mj, like energy of 20 joules or whatever, with a certain probability. And the probability is given by postulate of quantum theory by this number. That's a probability between 0 and 1. How do you get it? You take your state, in which you want to measure m, and you take the multiply this with the spectral projection p, you get a matrix, and you take the trace of that. That's a number between 0 and 1, and quantum theory tells you this is the probability for the measurement outcome to be mj if you are in the state rho. Okay? And it's crazy because if you give me twice exactly the same state rho, one row here, the other row here, exactly the same state, and I measure exactly the same quantity, like energy. These are the same states. I measure here, I get some outcome, and generally here, I get a different outcome, because it's probabilistic. So it's totally crazy, right? But that's quantum theory. That's not very classically intuitive. So there's an inherent randomness in this theory. Okay, so this tells you how to get, what you can get as an outcome and how probable each outcome is. And then there is a second part to this measurement postulate, and it says that if you made a measurement and it turns out that your meter showed the outcome mj, so you have realized mj, this has been measured, then right after, the state of your system will collapse into a new state, which is given by this quantity here. It's called the collapse of the wave function. What will you collapse into once you know that you have measured mj? You will collapse into a new state, which is the original state before you measured. Then you have to put on the left and the right the spectral projections of what you measured, and you have to normalize it so that this thing has trace 1. Okay? That's the measurement postulate. So again, what I measure is random, and so which state I collapse to after the measurement is also a random state. This comes with a certain probability pj. So if I look at the average state after a measurement, I have to add over these guys with the corresponding weights pj. And when you do that, oops, great, then you get what's called a non-selective measurement process. So again, I measure M in the state rho. The state rho is given, fixed at the beginning. I measure the observable M. I get, with probability Pj, this state as an output. And so if I take the average over all outputs with the corresponding probabilities, well, I have to add. I have to multiply this with Pj, small pj, and add up. So I get this. And this process, or this map state goes to this here, is called non-selective measurement process. Okay? So, thank you. There is one more postulate in quantum theory, which really makes the whole theory kind of interesting. And it says the following. Well, you know, if I have a spin or a qubit or something, and I place it on a table, then, or whatever, I shine light on it, then I have two systems. I have the spin and I have the light. So let's say I know what the Hilbert space of the light is, I know what the Hilbert space of the qubit is, but what is it if I take them together because they want to interact? The postulate of quantum theory is, if you look at composed systems of two parts, whatever they are, one is called system here and one has the index R for reservoir, then you have, again, this is a new quantum system, so it has to be given by a state space, which is a Hilbert space. What should this Hilbert space be? Quantum theory tells you it should be the tensor product of the individual Hilbert spaces. And then you should have a total operator, Hamiltonian, Hermitian matrix, self-adjoint operator on this thing, which generates the dynamics, which represents the energy. So typically, the system has its own energy. If it doesn't see the other part, the reservoir has its own energy. And then there is some interaction energy, which is an operator acting on both tensor products, tensor factors. Okay, so typically a Hamiltonian looks like this. And so because of this term V, this makes the system and the reservoir interact. So, you know, you can exchange here, I don't know, energy, particles, information, correlation, whatever. So this setup is called open quantum system setup. So this system is an open quantum system because it is linked, it is in interaction with something else. And the main problem, or the main interest in open quantum theory is to see what happens to this system if here I have something maybe very complicated but kind of generic. What is the dynamics of this system alone? Okay? That's the main problem of dynamics in open quantum theory. We go to the next slide. Okay. So here is about this dynamics. So that's the total Hilbert space of the bipartite system, the total Hamiltonian with the interaction. And I have a total state of the total complex system plus reservoir. And let's say I'm only interested in measuring an observable on the system alone. Because, you know, if I place a qubit on a table, I want to manipulate it somehow. I am not interested in the table. I'm only interested in what does the qubit do. If I want to do a measurement on the qubit alone, then, well, the whole system lives in the big Hilbert space, but I just have to look at observables M, which act trivially on the reservoir, because I'm not looking at the reservoir, okay? And so by the previous postulates, actually the average, if you look at the probabilities I had before and you look at the average of the measurement outcome of M, is given by this trace of the state times the measurement operator. This is for the whole universe, system plus reservoir. But if you're only interested in the system alone, then you can ask yourself, well, can I just make appear quantities of the system only without the reservoir? And the answer is yes, you can. Because this here can be written as a trace over the system only, system Hilbert space, of a new density matrix rho bar times M. So this here only involves quantities of the system. The reservoir has been what people say traced out. And this new state rho bar is called the reduced density matrix of the system. In classical probability theory, this means it's the marginal of, you know, of a joint probability distribution. Okay? And how do you get this rho bar? You have to take the initial state, which lives on the whole Hilbert space, and you have to take what's called the partial trace. The partial trace is an operation which takes an operator on the big Hilbert space, and then you apply the partial trace, and then the output is an operator only on the system Hilbert space. Okay? So the dynamics, you see, if this depends on time, then this will depend on time. And the big question often is, what is the evolution equation of this? Because it's very complicated, right? I mean, it looks simple, but you know, this guy must feel somehow the dynamics, or even this state alone, must incorporate all the properties of the reservoir. This has been traced out, but this is a very complicated object because it incorporates the reservoir and the interaction, it incorporates everything. Okay, let's skip this slide. Okay, let me come to the quantum Zeno effect. By the way, maybe if anybody has questions or if I'm saying something wrong, then just tell me, okay? Okay, so the quantum Zeno effect can be just, you know, expressed in words like that. It says, if I have a quantum system and I look very strongly at it, a quantum system that moves, that does something, but I look very, very intently at it, then I make this quantum system stop in its movement, it freezes, just because I look at it, okay? And if I look at it somewhat intently with lots of, you know, focus, but not infinitely focused, then the dynamics will just slow down. But in the limit, when I look extremely intently, then I freeze the system dynamics.
Is that when people say you observe and then...
Yes, yes. Oh, I said look at it. It's the same as observe something. It's the same as measuring something and get a readout. It's all the same in what I say. So if I measure something very frequently, if I look at the spin that does some chaotic stuff, I don't know what, but I look at it, I measure it frequently, then it will just stop and freeze. Okay, so this is actually has been verified in experiments, in labs, in real life, you know, in atom excitation and de-excitation processes. So famous physics experiments are, if you have an atom that can have an excited electron, for example, these are two energy levels. So if an atom starts out in an excited state where an electron has a lot of energy, and then you wait for a while, then this electron will fall down to a lower energy state, and then it will liberate some energy, the difference here, and this will be liberated as a photon that gets emitted into the field. Just a, you know, emission process. And for certain materials where you have certain atoms, you can actually, you know, measure how long this process does. If you start off with the excited atom, how many microseconds or whatever, picoseconds do I have to wait till this guy goes down and I see the photon that comes out? Physically accessible numbers. And so there's a time of the process, call it tau naught. Yes?
In physics, we consider the measurement problem, which is the fact that you have the evolution by the Schrödinger and the measurement. So measurement already break the evolution.
Yes, yes.
So, and freeze the state
yes.
in one of the end states.
Yes.
So, what is the Zeno effect in relation with this? Because you already have a freezing of the state with the measurement.
You mean, but if you do, you mean you have a wave function collapse?
Yes, yes.
So if you measure once, yes, you have a wave function collapse, but then the dynamics continues. I will explain. I look at the process where I measure once, and then again, and then again, and then again. And each time you measure, you could have a different output. So each time you would have a different collapse into a different state, so you would have a non-trivial dynamics, even though you measure, right? Because each time you collapse to a different, according to, okay? But the point here is, no, you will actually freeze the dynamics. Yes, but I'm not measuring here right now yet. It depends on the frequency, on how often I measure, yes. Yeah. No, but I will come to this. I'm just saying that there are these experiments. There is no measurement here yet, right? Well, I guess I will measure the atom, the emitted photon, because I have to see it. But this doesn't have to do with this part. I'm just saying, excited atoms get de-excited, they emit photons, and for a given material, you have a given time of the process. What happens if I now look, if I look at this situation, and looking at this situation means, for example, I don't know, in labs they know how to do it, but you shine light on it, okay? Oops, wrong way.
Looking at the photon, but at the atom.
I didn't look at nothing so far. Now I'm looking at the whole thing, the whole world, at the whole process. Okay? This is a bit philosophical. I don't exactly know how they do it in a lab, okay? But philosophically, if they make this whole thing interact with some laser, so you look at it, and let's say you shine a strong laser light on it, this means you observe very intently, then you can again measure this excitation time, I mean the time of the process, and you see, the stronger you look at it, that is, the stronger the light is that you shine on it, the slower the process will happen, okay? So you slow down this process by looking at it, which means in this example, by shining a light on it, which might mean by measuring it somehow, okay? So this is experimentally verified. Okay, so how do you write this in a formula? Basically, okay, so the whole story of my talk is this. Mathematical physicists have written down formulas to describe this in a sort of, to my mind, ad hoc way, which is what I'm showing now. And then I propose a different way of looking at this, which shows the Zeno effect in a more natural way, okay? So what's this ad hoc way? I make frequent repeated measurements. So here is time from 0 to some time t. And I give myself a number n, so that every 1 over n seconds I make a measurement. I make a measurement here, another here, another here, another here. And I make this non-projective measurement that I introduced before. This was this curly p. Okay? So n times I act on my initial state rho. That's the dynamics I'm looking at. N times I act with this one-step operator. What's this one-step operator? This one-step operator is first, you just evolve your system according to its usual, free, non-measured, unitary dynamics. Okay, that's this U. I just take a state, I let it evolve by not looking at it for t over n seconds, n is going to be large, for a short time, and then I make this measurement. This measurement is given by this non-projective measurement, which was this operator, which we had before. Okay, this represents a measurement. This is one step in the dynamics, and then I do this n times. So I let it evolve, I measure. I let it evolve freely again, I measure. I let it evolve freely, I measure. Okay? And then I get a density matrix, which depends on how frequently I measure and what the total time is that I arrive at the end. And what you want to do is, you want to see, well, I do this maybe for 1 hour, so t is 1 hour, but I increased my frequency of measurement, so n becomes very large, because then 1 over n here becomes very small. So the mathematical question is, what is the limit of this thing as n goes to infinity for t fixed? And this is actually not very difficult to do, at least in finite dimensions. It's an exercise. Trying to get to the next.
So the number of measurements increases.
Yes.
Per unit of time.
Yes. Okay. And so some people, this is just an exercise in linear algebra, kind of. In 76, Misra and Sudarshan were the first one looking at that, and there was a whole school of Italian physicists, mathematical physicists who looked at that. And the result is this. T is fixed, I measure increasingly more frequently, and this has a limit, has a density matrix, and the limit is the right-hand side here. What is the right-hand side? Well, this is the initial state, and then, okay, so this measurement was relative to some particular observable. This particular observable had these spectral projections, right? So I must take this initial density matrix in which I, to the left and the right, apply these spectral projections, and I add up all the projections. This gave me this operator script P, which was this non-selective measurement. So I have to first do a non-selective measurement on the initial state rho, and then I have a new dynamics, which is given by a new Hamiltonian called the Zeno Hamiltonian. And what's the Zeno Hamiltonian? It's just the original Hamiltonian when there was no measurement, but not quite. You have to also apply this procedure here to the Hamiltonian. You get another self-adjoint operator. This is the new generator of the dynamics. So what this means is that in the limit of infinitely frequent measurements, which means n goes to infinity, the dynamics is decoupled into so-called Zeno subspaces. Okay? Let me explain what this means. You see, I have these projections, right? These eigenprojections of the observables that I'm measuring. And they all add up to the identity, because that's what it is. If you have a Hermitian matrix and you add up all the eigenprojections, you get the identity. So the Hilbert space is decomposed into orthogonal subspaces, which are the eigenspaces of the measurement observable. So if I originally have a Hamiltonian, I can, think of it as being as having blocks that map from, let's say, P2 to P1. That would be this block, or for P3 to P4, I guess that would be this block, and so on. I mean, any H has such a block decomposition once the P's are given. And what's the action of this non-selective measurement? It takes H into the sum of Pj. This means that you transform this operator into a new operator where you leave the diagonal blocks the same, and all the off-diagonal blocks you put to 0. Because it's only Pj, operator Pj, not Pj, operator Pk, for k not equal to j. Okay? And so, when you have an operator like this, then you have invariant subspaces, right? This is an invariant subspaces, this and this. Each of these spectral subspaces are invariant subspaces. So that's the result. The Zeno, in the Zeno limit, n goes to infinity, the dynamics is decomposed into these subspaces. What does this have to do with not moving at all? Well, if the eigenvalues, okay, if these projections have rank 1, these are the spectral projections of the operator you measure, this means that the eigenvalues of this matrix that you're measuring are simple, they have degeneracy 1. Then these are 1 by 1 blocks. And in 1 by 1 blocks, e to the ith in a 1 by 1 block is just a phase and it goes away. And so in generic cases where eigenvalues are simple, this hz this hz is just a phase, and so it goes away, and the dynamics becomes totally time independent. That's why it freezes. Okay? Okay, I'm trying to go forward. So that's the Zeno effect. Now, okay. Now, I think this is artificial in the following sense. When you look at this dynamics, you just say, okay, I look at U, the free dynamics over for a small interval of time, then I apply by some miracle this measurement process, and then I iterate this. But what does it mean to apply the measurement process, right? This was just sort of a mathematical model, I guess. Well, so this P was introduced by hand in the dynamics, and you got this result. But what does it really mean? I mean, not that I actually know, but what does it mean to measure in a lab? Well, if I want to measure, I must have my measurement apparatus, which has some sort of, needle that tells me the outcome. And then I have to bring my measurement apparatus in contact with what I want to measure. And then, and then there is a reaction between the two, and then I can have a readout. So there should be in this description somehow, I think, the measurement apparatus, which was not there previously. It was just this P put in by hand. So really, instead of looking at the model we had before, I think you should take your system S and make it interact with another system which will model your measurement apparatus, take some interaction, and see what happens to the dynamics. Now, what would it mean in this situation to have very frequent measurement? Well, I guess frequent measurement is equivalent somehow to having those two guys interacting very strongly, with an interaction that is big, because it means it really, well, that's the feeling I think that you could get. Okay? So that's exactly what I said. Strong interaction in this open system situation where you have two systems and one system is the measurement apparent. The question is that, can this induce the Zeno effect? And this is our contribution. We show that this is actually correct. Let me check the time. Okay. Oh, yeah, so this is what we wrote in this paper together with Stefano Marcantoni, who used to be in Nice in France and who is now in Italy, in L'Aquila. And I don't know if you know this journal, but this is an open, what's it called? A free, like a non-subscription, open access journal that publishes a lot of quantum stuff. So we published this last year there. Okay, and what did we publish? Oops. All right. So we take a model of a small system interacting with a measurement apparatus, and we make them interact very strongly, and we look at what is the dynamics of the system alone in the limit of infinite strength interaction. And what we show is that, indeed, you get the Zeno dynamics. So what is the microscopic model? It's very common in the theory of open quantum systems. Maybe you've heard about this spin boson model, okay? Namely, a spin or a finite level system is coupled to a Bose field, which means just a bunch of linear oscillators. And that, yes?
This means that you will model the circuit as a standard dynamic with the reservoir.
I will model what?
As an interaction between
yes.
the reservoir.
Yes.
Using the standard dynamic.
I will see.
Standard Schrodinger or whatever. No?
Well, I will tell you, okay? Okay, so the system and the reservoir, which is the measurement apparatus in this situation, again, the system has its own energy, the reservoir has its own energy, and then they interact. How do they interact? Via an operator G, or a matrix G that acts on this part, and an operator phi of G, whatever that is, that acts on the reservoir part. Now, what is the system? For the system, I take an n-level system, like if n is equal to 2. Oh, that n is not the n from the previous measurement thing. That's just a different thing. If n is equal to 2, you would have a spin. If n is equal to whatever, you have an n-level system. And so this is finite dimensional in our analysis for now. And the reservoir should be something big, because you see, well, the philosophy is that the measurement apparatus should be very complex and sort of kind of generic. And so this is a very big system, and we take a bosonic field. So lots and lots and lots, an uncountable number actually, of quantum oscillators, indexed by k, if you wish, that's a frequency or a wave vector. And for each k, you get a harmonic oscillator. I mean, I'm not going to explain this, it's just, and you have here, the interaction is given by this operator here. This can create an excitation of the oscillator number k, and the corresponding term, this is Hermitian conjugate, can annihilate an excitation. And so you exchange energy between the system and the reservoir, and there's a tuning parameter g of k, which is just a number which tells you how strongly the mode k interacts with your system S. If for some k g of k is 0, it means the corresponding mode with this k is not interacting, and so on. Okay? So I'm not going to discuss too much the aspect of the bosonic field. It's kind of standard. And this operator G here, it's a matrix, as I said, on HS. It's a Hermitian matrix, and so it has a spectral decomposition. This is eigenvalues gamma and eigenvectors and eigenprojections p. Okay, this smells like, I write this because this smells like this will be measured. And indeed, we show that what is going to be measured is this G. And according to this G, you get the Zeno dynamics. Now, there is this important prefactor here, lambda, which is a real number, which is a coupling constant. If lambda is equal to 0, you don't have this part. The system and the reservoir, they evolve independently. They don't interact. Nothing interesting happens to the system dynamics. If lambda is very large, then we call this strong coupling. And our question is, what happens to the dynamics of the system when lambda goes to infinity? Okay, so what we're interested in is this quantity here. That's the system dynamics, the reduced system dynamics. You're obtaining by taking first an initial state of a system and the reservoir. So the system can initially be in any state you like. And the reservoir is in a state, in a density matrix rho r. And for rho r, well, you know, if you want to do some calculations and proofs, you have to sometimes restrict. You have to have a little bit of an idea what this is. And we take a class of Gaussian reservoir states. Whatever that means, this is a Gaussian state of a quantum field. Examples here that are covered by this is a temperature state. If the Gaussian field is at any temperature, that goes here, or similar. Okay? And so initially, the system and the reservoir, they are uncoupled, not entangled. This is the initial state of the whole complex. Then you let this initial state evolve. This is the whole system plus reservoir state at time t. Again, this H is the energy of the system plus the energy of the reservoir plus lambda times the interaction, and lambda will be large. I don't show the lambda here. Okay? So this is what we want to do. This is what we want to look at, and we want to look at the limit for t fixed, the limit as lambda goes to infinity. Again, lambda is hidden in here because it's hidden in the Hamiltonian because it governs the strength of the interaction. Okay. Okay. And this is our result. It's actually a theorem. For all time fixed, the limit of this object we just had above, when the coupling goes to infinity, oh my God, it's this here. What is this? You take your initial system state, you apply to it the non-selective measurement process according to which observable? The observable belonging to P, that was the interaction, right? The interaction was, oh, this is not good. You see, when you want it to change, it doesn't, and
Maybe you should go to the whiteboard. Just to get that.
Ah, smart. Ah, must be a professor. So there was the interaction was lambda g times this phi of g. And this lambda had spectral decomposition gamma n Pn. Okay? And so this interaction operator is actually what gets measured in the ultra-strong coupling limit. Ultra-strong meaning that lambda goes to infinity. So indeed, you recover the quantum Zeno effect, not by putting in by hand this non-selective measurement, but by actually coupling your system strongly to a quite generic reservoir.
There are two parameters for when you are putting the strength of the magnitude of the interaction. One is lambda.
Yes.
And the other one is the small function g.
Yes. Let's say g has L2 norm 1.
Okay. Where is the action of g here? It doesn't appear?
Nope. That's another thing. This is very generic. What you get out as a result, you know, where is the reservoir here? Where is the influence of the reservoir? It's not here anymore. It evaporated. It's very generic.
What is the meaning?
Hmm?
What is the meaning of that?
The meaning is that if you couple very strongly to virtually anything, but of course, this only, if I took here a finite but large lambda, I would get something which depends on the reservoir properties. So in a sense, this is maybe a little bit artificial, this is kind of mathematical. But the meaning is that if I couple extremely strongly with pretty much any kind of noise, the noise will become generic. The effect will become generic. The details of the noise don't play a role. This happens. Okay? Okay. Do you like the colors? So, this is the message. The dynamics of these ad hoc models where you put this P in by hand and you measure very frequently is the same in the limit of in their limit it was measure infinitely frequently. In our limit is couple infinitely strongly. It's the same as the dynamics of open systems strongly coupled to quantum reservoirs, and it's the same as the Zeno dynamics.
So, what is the difference between this and making only one zoom? Because you take the same single zoom or just one zoom.
No. If you make one measurement, no. If you make one measurement, yes, you will have a collapse. But then you evolve again. You evolve again with the interaction with the field, right? It's very complicated.
It looks clear that you are modeling instrument that has a strong interaction with the
Yes.
system and the result.
Yes.
And you take exactly the same result.
Yes.
So this applies for just one zone.
Well, I mean, I don't really
You
make...
incorporate here this frequently measurement system.
No, I just,
This part of the center.
It's only in the limit that these two coincide. If
but making one measurement, you need an interaction is very weak, and then
Yes.
you make it strong,
Why?
and then you make it very weak.
Because
No.
the resonance breaks fully the standard dynamics.
No. Yes, it's a good question. But look, I am not making a measurement.
Yeah.
They make a measurement. I couple to a reservoir, which to me seems, that should mean a resonance. And I'm saying that it is the same result, at least in the regime of very strongly coupling and very frequently measuring.
Yes. This is the part of, I don't really understand, because for me, it's the same. So I agree with you with the first
Yes.
part, but this is the same in the case of one measurement.
No. In the case of one measurement,
Change the magnitude of the coupling and keep
Yes.
it constant. But it's making one measurement means take a very weak coupling,
Yes.
because your device is not connected, and then
It
you
is not weak in one measurement. It's really strong.
no, but they don't have a coupling. I only have a coupling.
Yeah, I agree with that.
But if I wanted to look what happens after only one measurement, I think I agree. You should take the lambda to be small. Well, feeling. Now, this is a theorem, okay? The other thing is feeling.
I like that because in some way it solves the resolution problem.
Yes?
From
Yes?
physics. It solves the problem.
Well, yes.
You don't need to talk about the frequency.
Yes. In this model it does, I see. Okay, so now, you have to tell me, because it's 20 after. I can give you an outline of the proof. It's a few slides. Do we have time, or otherwise we can just... Okay. I lose a lot of time trying to... Okay. So, what we are interested, yet again, is this quantity. That's the initial state. That's the dynamics after it has interacted between these two guys for time t. That's the full dynamics. I have to take the marginal, because I'm only interested in the dynamics of the system, which means take the partial trace over the reservoir. This is the generator of the dynamics H. System energy, measurement apparatus, reservoir energy, interaction, lambda large. You see, if you do a small coupling perturbation theory, you would say, in first order, I neglect this, and then I have the free dynamics, and then I look what the effect is for large lambda. But that's not for small lambda. But that's not the case here. Here we are interested in lambda very, very large. So we must do a different kind of approach. And so the idea is to look at this together, which incorporates lambda at any size, okay? Look at this together, call this operator k, that's another Hermitian operator, by just sort of thinking that this is not here. And then link, and it'll turn out that in the limit, when lambda becomes very large, the dynamics generated by k, so instead of h, you would have k here for lambda large, becomes quite simple. Okay? And then you have to relate the full dynamics with the dynamics of hs alone. So, I will show you why this becomes simple, but really what I need is this, right? That's what's up there. So how do you compare these two unitary groups where you have different generators? And the technique for that is very standard. It's called the Dyson series. Namely, one unitary group can be written as the other unitary group, but with some nasty looking operator in front. Okay? This is simple to obtain by repeatedly differentiating and integrating. Okay? It's a simple formula really, but it looks nasty. But the good thing, so you have a sum here, you have integrals over times, intermediate times, and you have these operators, the system Hamiltonian, which is time translated with respect to the with respect to the k dynamics. So the good part is that this is what you want, and let's say if you know the dynamics with k for some reason, which I show you why in a second, then all of these h's, they only involve the dynamics with k. So in a sense, even though the structure is complicated here, all the constituents are simple, okay? And so you trade off a more complicated structure versus an easier dynamics, and you have to handle this. So I will replace e to the I minus ith by this in the above formula. Right? This is what I really want. I replace e to the ith with e to the itk. I have these guys twice, so unfortunately I have two Dyson series here. Okay. So this looks complicated, and it is, because it has lots of terms. But again, only simple terms show up, because only the dynamics with respect to k here shows up. So the strategy is, first figure out why the dynamics here with k is easy when lambda is large. And then secondly, make sure that you can take the limit lambda goes to infinity in all these sums and stuff, because then this simplifies. And then you get a new series, which is simplified because you took lambda to infinity, and you use the knowledge that this is simple. Okay, you get a new series. It's still a bit horrible looking, but then you can see that this series actually can be resummed. It represents exactly the desired final result. Okay? The desired final result. Because the final result is also dynamics, e to the ithz. You can also do a Dyson expansion there, and you see that it coincides with the limit of this one. Okay? So, I'm going to explain you, that's pretty much, we're going to the end, don't worry. I explain you why this dynamics is easy. Okay, let's say I have a system operator x, and I look at the dynamics generated by this k. So I have to deal with this here. And again, this k is, I discarded the h system Hamiltonian, so it's the reservoir plus the interaction. Lambda is anything, but I have in mind lambda will be small, okay? And G has this spectral decomposition. So I'm using something which from linear algebra, if I add up all the eigenprojections, I get the identity, because this is a Hermitian matrix. Okay, and I use this identity, I stick it in here, and I stick it in here. That's why I get two sums, to the left with m, to the right with n, and I get these projections. And these projections then act on k. But that's the thing, right? If a projection, if one of these p, let's say this pn sits next to this K here. Look at what K is. This projection only acts on the system part. There is no part here, and it is an eigenprojection of G. So when the projection P sits here, Pn, it turns this Gn into the eigenvalue gamma n. Okay? So that's why I have replaced the non-commuting G's just by numbers gamma. The price to pay is that I have these extra projections here. And the good thing now is as well that this is factorized. This is completely factorized. See, this is not, well, the exponential of this is not factorized, but when I insert this, this is factorized. And now I have to take the marginal, the partial trace over the reservoir, which means just taking the partial trace over the density matrix of the reservoir of this. Okay? And the system operator has just become numbers. And if I take the partial trace, or the marginal, right, that's what I said. This was the term that was there with this gamma m and gamma m. If I take the average or the partial trace over the reservoir R, which is this Gaussian state, because it's Gaussian, you can calculate this explicitly. And what you get is this Gaussian or exponential of a quadratic in the differences between gamma n and gamma n. This is just because the state is Gaussian. Okay, so this becomes like that. It's quadratic in lambda gamma, so lambda squared, gamma squared. And then it is also time dependent, but this is a function of t. You don't care too much what it is. It's a non-zero function of t, if t is not zero. Okay, and so now you see, that's exquisitely good, because if I take lambda large, whenever m is not equal to n, this goes to 0. Okay? And if m is equal to n, this is just 1. So the ultra-strong limit selects in here, if I take the marginal, which is what I did before, and I take lambda to infinity, out of these two sums, it only takes a diagonal m is equal to n. And so that's the trademark of this Zeno effect, right? Because that implements this non-selective measurement. Okay? So the limit of this is now like that, and you see that's the action of the curly p, which is this non-selective measurement. Okay, so this is almost my last slide. So again, what I do is, that's what I had already on the slide before. It looks horrible, but I must make sure that I can take this limit in here, and I use what I just told you in each term in there, and then I get, again, a double series here, but this double series, I can resum to see that it's actually like this, because this I can also write as a series. Okay, and I see these are the same series, and then I'm done.
The convergence for each t fixed.
Yes, that's exactly right. Pointwise in t. For each t fixed, you take lambda to infinity. That's correct. Yeah. And so this is the upshot of what we did. The previous treatments of the Zeno effect, people looked at the dynamics interspersed with infinitely frequent measurements, and the measurement is introduced just as a formula with this script p. And nobody talks about what actually measuring means. And our approach is, instead of sticking in these p's in the formula, we implement the measurement, whatever that means, by connecting the system strongly to a bosonic quantum field. And we look at the limit where this field is infinitely strongly coupled. And the point is that the system dynamics in their approach and our approach is the same, and it's the Zeno dynamics. And as Eduardo pointed out, the system dynamics does not depend on the details of the reservoir. I mean, if it did, then this could never be equivalent to what the other people did, because in this, there is no properties of any reservoir there, right? There's just a P, so it must be generic. Okay, this is it, and I thank you for your attention.
We thank Professor Marco. I think we already have had a little discussion, but maybe we have time for one or two questions.
Students question.
Yep. Okay, we thank you.
All right. Muchas gracias.
Thank you. Sorry.
Yeah, no problem.
Thanks a lot.
Yeah, no, thank you.
Very nice.